Hi guys, welcome to the second half of 3.12. So in 3.12, in the last video, we started talking about sum and difference identities and double angle identities. And these will allow us to find more, evaluate more trig functions that maybe aren't exactly on the unit circle. So we did do a few examples with sum and difference. So we're going to jump into some double angle ones. Example 10 is a really important one. You do see these a lot. So I'd make sure that you understand what's going on here. So it says, suppose that sine of A, or alpha, is equal to 4 over 5 in quadrant 2. So I'm going to draw myself out a little triangle, opposite over hypotenuse. I'm going to go ahead and find that third side. A lot of you probably know that that's a 3, 4, 5 triangle, so that side will be 3. However, we want to be really careful because we went to the left. I need to label that as negative 3. You could also use Pythagorean theorem. All right, sine of B, or beta, is in quadrant 1, and so it's opposite over hypotenuse is 1/2. This is just an angle on my unit circle, so that's going to be square root of 3. You could also do 2 squared minus 1 squared gives me 3, and then take the square root. So this is alpha, and this is beta. And this is actually some more practice with sum and difference, and then we'll do one with double angle. Okay, so cosine of A here is adjacent over hypotenuse, so negative 3 over 5. And then cosine of B is root 3 over 2. So we'll just do one of these. Let's do cosine of alpha plus beta. So if I were to break this up using my formula, it'd be cosine A cosine B minus sine A sine B. Remember, cosine is opposite. So cosine of A, we said, was negative 3 over 5. Cosine of B is square root of 3 over 2. Minus sine of A, it told us in the problem, was 4 over 5. And sine of B was 1/2. So I end up getting negative 3 square root 3 over 10 minus 4 over 10. I'm not going to simplify 4 over 10 because I already have a common denominator there and I don't want to get rid of it. So I just end up minor simplification, just put it all over one common denominator. I would encourage you to try D on your own. I'm just going to put the answer here and check it. Okay. All right, now let's do one that's a double angle. So we're going to do example 12. It's the same idea. It tells us that cosine of theta equals 3/5, and it's in quadrant 4 because it's in between 3 pi over 2 and 2 pi. So I'm going to draw out my triangle. This is theta, and adjacent over hypotenuse. This is, again, a 3, 4, 5 triangle. Notice I'm labeling the opposite side as negative 4 because I'm going down. Sine is negative in quadrant 4. All right, so if I'm finding sine of 2u, that's the same as 2 cosine u sine u, or 2 sine cosine, doesn't matter. So when I plug in, cosine of u is 3/5, sine of u is negative 4/5, adjacent over hypotenuse and opposite over hypotenuse. I can multiply straight across. So 2 times 3 is 6, times negative 4 is negative 24 over 25. Cosine of 2u, okay, you can use any of them. I'm going to use the first one just because that's the one that I usually memorize. Cosine squared u minus sine squared u. Well, cosine squared u is just cosine of u squared. Cosine of u we said was 3/5, and I'm going to square it, minus negative 4/5 squared. So 3/5 squared is 9 over 25. You square the top, square the bottom. Be careful on this one. When I square negative 4, it's going to end up positive, so that would be minus 16 positive over 25. I have a common denominator, so I'm just going to subtract across the top, and I get negative 7 over 25. Okay. Now let's look at a couple examples where we did equations back in 3.10, but what if we had something like sine of 2x in there? How could we use our formulas? So number 14, okay, says sine of 2x plus cosine of x equals 0. So I know that sine of 2x has an identity, and that's equivalent to 2 sine of x cosine of x. So I'm going to go ahead and write that out. Once you get to this step right here, it should look exactly the same as what you did in 310. I have a GCF on both of cosine of x, so I'm going to factor that out. And now I'm going to set both of my factors equal to 0. So I'm going to say cosine of x could equal 0, or 2 sine of x plus 1 could equal 0. I'm going to go ahead and solve. All right, so we're thinking, where does cosine of x equal 0? It tells me the interval is 0 to 2 pi. Well, that's going to happen at the top and the bottom, so that's at pi over 2 and 3 pi over 2. And then where does sine of x equal negative 1/2? Well, that's going to happen in quadrants 3 and 4, and that will be right here and right here. And that is at 7 pi over 6 and 11 pi over 6. So knowing your identities will help you to solve some of these more complicated equations. If I rewrite this, then it starts to look exactly like what we've already done. All right, so example 16 is the last one we'll do in this video. Now, this one's a little bit harder because I have cosine of 2x. And remember, I had 3 options, okay? I had cosine squared of x minus sine squared of x. And then if I rewrote that as 1 minus sine squared, I got 1 minus 2 sine squared of x. Or if I rewrote this sine squared of x as 1 minus cosine squared of x, then I got 2 cosine squared of x minus 1. Now, it is important on an equation which one you pick, and I'll explain why. So on this, the other term that I see is sine of x. So I want to see if I can rewrite all of this in terms of sine of x, because when I have sine and cosine together, it gets pretty complicated pretty fast. So I want to pick the one that only has sine squared of x in it because my other term is sine of x. If my other term was cosine of x, I would probably want to pick the third one. This one doesn't usually help a ton in terms of equations, but like you could see on the previous one when we were doing a triangle, that was just as easy. So I'm going to rewrite this as 1 minus 2 sine squared of x because I want it in terms of sine of x. Copy the rest. And then plus 1. Okay, because I combined 1 minus 2. I'm going to move everything over to the right side because I don't want that negative in the very front. And then it just becomes a factoring problem. If it helps, you can rewrite them with your u's. Factor. I end up getting 2u minus 1 and u minus 1. When I set these equal to 0, I get u equals positive 1/2 and u equals 1. Well, what did u really represent? U represented sine of x here. So I'm going to go back and say I really want where sine of x equals 1/2 and sine of x equals 1. Let's start with sine of x equals 1 because that one's a little bit easier. That's where my y is equal to 1. That's going to happen at the top. So that's at pi over 2. And then sine of x equals 1/2, that's going to happen here and here. It's in the first and second quadrants in where you have a big X and a little y. So that's going to be at pi over 6. And then this angle right here is 5 pi over 6. So the big idea on this one, the hardest step is to get to this first one. It's to recognize I have cosine of 2x, so I know I need to rewrite that with an identity. And which identity do we pick? Well, on this one, because my other terms are sine, I want to rewrite it with only sine. So that's going to make my life a lot easier. If you chose one of the other ones, you're still going to have to do some manipulating to get there. And it's going to be a lot harder, and you're not going to be able to get to that step immediately. So make sure that you're identifying what else is in the problem and trying to rewrite it with that. Okay, that wraps up 312. Have a great rest of your day.